This is the second video for Learning Module 13 of the course Math for Electronics. In this video we go over the slides that cover the use of logarithms in the analysis of AC circuits. In the current textbook, that is going over chapter 23. One of the key applications of logarithms in electronics is in the measurement of gains from a circuit. Now, gains could be positive or negative. Positive gain means the output is larger than the input. Negative gain means the output is smaller than the input, at least when logarithms are used. Now when you're measuring gain of an electronic circuit, the symbol used is A. That is a capital A. Most times the gain is represented as a log of the ratio of the output quantity divided by the input quantity. Sometimes the gain is represented as a plain ratio. And in that case, the gain would be represented by a capital A. Most commonly, gain is analyzed in terms of power gain. That would be A with the subscript of P, or voltage gain, A with a V subscript. And as straight ratios, AV would be V out over Vn, AP would be power out over power in. The bell and the decibel units, they're derived from how a received signal is perceived, specifically by the human ear. The human ear is not a linear device, it is logarithmic. With two sounds, one perceived as being twice as loud, but by a human being, the louder sound actually has approximately 4 times the power. Units used to in that measurement is a bell, which was the original unit named in honor of Alexander Graham Bell. It was found out to be too large. The decibel, which is 1/10 of a bell, is the most commonly used unit for logarithmic gain. Okay, now let's go back over power gain. In particular, relative power gain, AP equals P out over Pn, where P out and Pn are specified in watts. The gain can be the same for different pairs of values of P out and Pn. Now, like I mentioned before, this is usually expressed logarithmically, and it's through the use of something called using the units decibels. In particular, power gain measured in decibels would be A with a subscript of P dB, as shown. AP dB equals 10 times the log of the power gain. And many times, unfortunately, dB is left off. In other words, it's given as AP and the answer is given in terms of dB. If that's the case, somebody left these dBs off the AP. Now, in terms of power in and power out, AP is actually power out divided by power input. In other words, we replace the A with this fraction. And the answer is in terms of dBs or decibels. Okay, so in its simplest form, removing, let's see, APdB equals 10 log of P out over Pn. And if we go and modify this equation, we're going to divide both sides by 10. We're left with APdB divided by 10 equals the log of power out over power in. Now the next thing we're going to do is we're going to take the anti-log of both sides. And in order to take the anti-log of the log is we're going to take this expression and make it the exponent of the 10, and we're going to take this expression, this term, and make it the exponent of 10. Okay, And there we have it. So 10 raised to the power of APdB divided by 10 is equal to power out over power in, or AP. And again, just for a refresher, if you take the log of some quantity and make that the exponent of the 10, you're left with that original quantity. Let's look at some example problems. The power out of an amplifier is known to be 30 watts. The input power is known to be 100 milliwatts. What is the power gain in decibels? So, simplest form, APdB would equal 10 times the log of 30 watts divided by 100 milliwatts, and that would be 10 times the log of 300. You can plug 300 into your calculator and run the log function on it, and you'll come out with 2.48, which when you multiply it by 10 becomes 24.8 dB. Let's take a look at another problem. It comes at it from a different aspect. You're given you're given the power output of the amplifier expressed in dBs and the input power, and you're asked to find the output power. So we go and put the dBs in for APdB, that's 40 dB, times 10 log of power out over 50 microwatts, which is power in. We divide both sides of this equation by 10. We're left with 40 dB divided by 10, or 40 divided by 10, and the log of power out divided by 50 microwatts. Now we take both sides of this equation as the exponent of 10. We're left with this, and we're left with power out. And 40 divided by 10 is 10 to the fourth, which is 10,000. So that's where that comes from. So P out, so we got P out over 50 microwatts equals 10,000. Multiply both sides by 50 microwatts, which is what we have here. Power out equals 50 microwatts times 10K, which would come out to be 0.5 watts. Let's look at another example. We're given the output power and the power into an amplifier, and we're asked to find the gain as a ratio and the gain in terms of dB. So let's start off real simple. Again, as review, power gain as a ratio is power out divided by power in. Plug in the values, 2.75 watts divided by 50 milliwatts. So this becomes 2.75 divided by 0.050, or 55. And APdB would be 10 log AP, or 10 log power out over power in, or since we already know what this ratio is, and we know what AP is, it's 55, let's put that in there. Take the log of 55, it'll be 1.74, then multiply that by 10, so 17.4 dB. Now let's take a look at another one where we're given the power out and the power gain in dB, and we're asked to find the power in. So power out, APdB would be 25 dB, 10 log of AP, divide both sides of this equation by 10, we're left with 25 dB divided by 10 equals the log of AP, and 10 log of AP equals AP. And 10 to the 25 over 10, or if you prefer 10 to the 2.5, equals 316.2. So there's 316.2 equals AP. 316.2 equals power out over power in. 2.75 watts over power in. Multiply both sides of this equation by power in, divide both sides by 316, and you're left with Okay, let's go over how we derive how the equation for voltage gain in dB is derived from the one for power. Because the voltage gain version of power of AV dB depends upon the input and output impedances of a circuit being exactly equal. If they're not, you have to rely on the power equation, the power version, instead of the voltage gain. So let's start off by dividing power out is equal to V out squared divided by R out, and power in is V in squared divided by R in. And APdB is 10 log AP, which would be 10 log power out over power in. And when we substitute these for power in and power out, we're left with 10 log of, the numerator is V out squared divided by R out. The denominator will be V in squared divided by R in. Now this can be rewritten as, you go and simplify this fraction, it becomes 10 log of V out squared divided by V in squared times R in divided by R out. And since we're dealing with the log of a product, this can be rewritten as 10 log V out squared divided by V in squared plus 10 log of R in divided by R out. Now the rest of these equations follow if R in equals R out. This second term becomes R in R divided by R out when they're equal becomes 1, and the log of 1 is 0. So we're left with 10 log of V out divided by V in squared plus 0. So just drop it. And this squared here, if you put it out here, you can multiply that times 10, and 2 times 10 log of V out over V in equals 10 log of V out divided by V in squared. And this then goes to 20 log of V out over V in will give you power out. It'll also, in the case where V in and V out, when R in and R out are equal, that power out is also, besides APdB, it is also AVdB at the same time. So AVdB equals 20 log of AV, or if you prefer, replace AV by what it consists of. That would be 20 log voltage out over voltage in. Of course, the units are dB, which stands for decibels. Now, given this, let's divide both sides by 20. We're left with, given this equation, let's divide both sides by 20. We're left with AV dB divided by 20 equals the log of V out divided by V in. Now, if we take the analog of this side, in other words, make this the exponent of the 10, we have to make this the exponent of the 10. This is what we have here. 10 with an exponent of AV dV divided by 20 equals V out over V in, which of course, if you remember, equals voltage gain. And this is a useful way, this would be the exponential version of this. So when given an input and output voltages, use the standard given equation, AVdB equals 20 log V out over V in. When given AV in dBs, you use this version of the equation to find AV, and if you have either V in or V out after you have AV, you can find the missing one. Example problem. The output voltage of an amplifier is 1.73 volts. The input voltage is 50 millivolts. Assuming that Rn equals R out, find voltage gain in dB. That would be AV dB equals 20 log V out of Vn. 1.73 divided by 50 millivolts, which would be 30.6. Take the log of that and then multiply by 20. And the answer comes out to 30.8 dB. Let's say the voltage gain of the device is given as minus 6 dB and the output voltage is 700 millivolts. You're asked to find Vn. Let's go plug in what we want, what we have. You can plug it in this form and then divide both sides by 20, or else you can plug it in here. So we got minus 6 dB divided by 20 equals the log of 700 millivolts divided by Vn, which simplifies to minus 0.3 equals the log of 70 millivolts divided by Vn. Make both sides of this equation the exponent of 10, and you're left with 0.501 equals 700 millivolts divided by Vn, and Vn will equal 1.4 volts. Of course, the input is larger than the output, and the reason why I knew this back here is because the voltage gain of the device is a negative number of dBs. Now, voltage gain or power gain in dBs has the same characteristics as the gain in ratio. They represent an infinite set of output quantities divided by input quantities. All you're dealing with is a ratio. For power, if you always have power in as 1 millivolt, then you have a logarithmic way to represent a particular power. And one of the reasons that you might want to do this is if it's an extremely small power or an extremely large power in which there are a lot of zeros. And it's very easy to make a mistake with a lot of zeros because you lose track in counting them. Another reason is many physical systems, such as the human ear or power levels in electronic circuits, cover a very wide range. For example, human hearing covers a range of 120 dBs from the threshold of hearing. That is where the sound is so low you can just first hear it, to where the sound is so loud it causes pain in your ears. And 120 dBs is 1 followed by 12 zeros. You could easily write 11 or 13 and not know you made a mistake. Now, power levels in decibels in electronics are usually referenced to 1 milliwatts, and the units are dBms. dB for decibels, and M being for milliwatt reference. So power levels reference to 1 milliwatt would be AP dBm equals 10 log of whatever the power is you want to represent logarithmically divided by 1 milliwatt. Now to go to the other way, P equals 1 milliwatt times 10 to the PB divided by 10. Sometimes the terminology is off a bit. The given, for example, problem 23.5 on page 476 is typical. Other types of errors also occur. The given was the power output of an amplifier is 33 dB. It should have been 33 dBm. Now the gain of an amplifier is the power out over input power. dBm is a ratio of power in watts reference to 1 milliwatt. Again. And here's the equations. Let's take a look at an example problem having these equations above. The power output of an amplifier is 33 dBm. Determine the output power in watts. APdBm equals 10 log P over 1 milliwatt equals 33 dBm. Let's take this equation here. 33 dBm equals 10 log of power out, of power divided by 1 milliwatt. Divide both sides by 10, we're left with 33 dBm divided by 10 equals log of P divided by 1 milliwatts. Take both sides of this equation, make them exponents of 10, and you're left with, for this side, you're left with P divided by 1 milliwatt equals 10 with an exponent with this as the exponent. Then multiply both sides by 1 milliwatt and you're left with P equals 1 milliwatt times 10 with the exponent of 33 dBm divided by 10. Drop the dBm. Since we're dealing with ratios, divide 33 by 10. So we're left with power equals 1 milliwatt times 10 to the 3.3, which is 2 watts. Reference levels. Remember, read carefully because the usage of terminology is commonly off by a bit. Somebody drops leaving the M off of the dB. Somebody leaves the D off of power gain. And you can see by the calculations they're giving power, they're giving gain is A equals so many dBs. You say, oh, there should have been a dB there as a subscript for A. Or they leave off the M when they're saying the power output is 33 dB. What is that power in watts? Or something similar where that's one of the stages of calculation. Obviously they left the M off in the reference because you can't find the power if it wasn't a reference to dBm like that. Now let's look at another use for logarithms in the analysis of AC circuits. One is a graphical method. It involves plotting on a specific type of graph paper along with calculating the gain in dBs. Useful tool, and Bode plots are a useful tool for approximating the frequency response of a circuit or a system over a wide range of frequency. Usually uses voltage gain calculated in dBs and semi-log paper. What is semi-log paper? What you see here is semi-log paper. If you notice on the vertical axis, the lines are marked off in a linear manner. The space between these two lines is the same as the space between these two lines. On the horizontal axis, the lines are marked off in a logarithmic pattern. In other words, the first box here is next to its right is a smaller box and a smaller box and a smaller and smaller until you get all the way down here. Actually, there are 10 little boxes here. And then that large one reappears after the smallest one, and the thing happens over. Now, on this particular representation of semi-log paper, this cycle of large to small, where there are 10 lines involved, happens 6 times. This is known as 6-cycle semi-log paper. Gains in decibels are noted on the vertical axis on the linear scale. The frequency is on the horizontal axis. Now, the frequency scales can be overlaid to match a given problem. For example, if we look here, we start off here with 10 hertz, 100 hertz, 1,000, 10K, 100K, 1 million. And this would be 10 million over here. And the dBs are laid out linearly. Let's see, let's say this is a 0 dB line. You go down 5 and you're at minus 10. You go down 5 more, you're at minus 20. Go down 5 more, you're at minus 30. This bottom line here would be minus 40. Now, if you go back up here to the minus 10, and you go up 5, you're at 0. Also notice that if you go down 1.5 subgraduations, you are at minus 3 dB. So that tells you each one of these subgrads is 2 dB difference. Now, this is a 0 dB, and if we go up 5, we'd be at positive 10 dB. Interesting thing to note, this minus 3 dB point corresponds over here to a voltage gain of 0.707. Now, an example of what I'm saying is the frequency stayed the same down here, but let's take a look at the gains. This is a gain of 10. At this, you go up 5 from the bottom, you're at 10, then you go up 5 more, you're at 15. So this must have been 5 dB. You can start it wherever it makes sense for what you're plotting. This is 10, you go up 5, you're at 15, 5 more, 20, 25, 30. And you say, well, what about the gains between 5 and 0? Obviously, this plot was shifted because the data is going to be in this area. So it's a snapshot of an infinite size piece of semi-log paper that is of this, it has this range on it. You can move this, slide this thing wherever is appropriate for plotting your data. Applications. Remember our high-pass filter from before? Let's see, we have a 200 nanofarad capacitor and a resistor of 7.96 K ohms. And the voltage out from this high-pass filter would be equal to the voltage across that resistor. Now, if Vn equals 10 volts, AVdB would be 20 times the log of voltage out over voltage in. At high frequencies, X sub C is approximately equal to 0. And so at very high frequencies, if X sub C is about equal to 0, there'll be almost no voltage dropped across here. The voltage dropped across the resistor will be approximately equal or very close to, so close to 10 volts it doesn't make much difference. So the output will be 10 volts, the input would be 10 volts. You're left with the log of 1, and the log of 1 is 0. And no matter what you multiply it, it'll be 0. At the cutoff frequency, or FCO or FC, depending on how you remember it, that happens when the magnitude of R equals the magnitude of X sub C. And that happens, if you remember, at a frequency, the frequency at which that happens is equal to 1 divided by 2 pi times the value of the resistor times the value of the capacitor, and you run that calculation, it'll come out and give you the frequency at which the magnitude of R equals the magnitude of X of C. That is the cutoff frequency. And in this particular case, using those values, it'll be 100 Hertz. And again, high pass filter, straight line approximation of how this runs would be, and we'll go from that point. Go from that point in a straight line to minus 6 dB at 50 Hertz. So we got 100 Hertz. Let's find 50. That would be 10. That'd be 10. That'd be 20, 30, 40, 50. And it'd be minus 6 here. Since this is minus 20, that's 0. 10 would be there. 6. The gain declines by 6 dB each time the frequency is cut in half, or 20 dBs when it declines by a factor of 10. So when the frequency goes from 100 Hertz to 10 Hertz, the frequency goes down. The actual gain is F. Now, on a filter, the straight line also goes to the right. Straight line approximation for frequencies above 100. The approximation would be a gain of 0 for all frequencies higher than 100. So, and we draw a red line here. Now the actual gain at the cutoff frequency, the knee frequency, would be 3 dBs below the straight line approximation. So it'd be about right here. Okay. At the cutoff frequency, you'll find the greatest difference between the straight line approximation and the actual gain calculated or measured. And that difference is, like I already said, 3 dB lower. Amplifier gain. Amplifiers have lower and upper cutoff frequencies. In between those two frequencies, the gain is somewhat more flat. And for an example, we're going to be looking at plotted out. The mid-frequency gain is 25 dB. Let's see this plotted out. So mid-frequency gain would be 25 dB. If we go down, now, lower cutoff frequency, or FL, F1 would be 90 Hertz. The upper cutoff frequency would be 12 kHz. So straight line from 90 Hertz to 12 kHz, okay, would be the way it operates. Now, if we drop down, if the frequency drops in half to 45, the power output would be 6 dB lower, would be minus 19 dB. Same thing happens at 12 kHz, at 24 kHz, or twice the frequency. The output gain would be down 6 dB. Now, at both of these cutoff frequency or knee frequencies, the actual gain would be 3 dB lower, so it would be 22 dB, about halfway, but the actual gain would be here. So the actual gain, whether measured or plotted, will always be on the inside of these lines. And the place where they're most off is right at the knee frequency. They're 3 dB lower. Now, as to the chapter homework and the quiz or the final questions, you should not see much more than concept questions and simple questions asking what is the cutoff frequency, what is the knee frequency, or the cutoff or knee frequency is the half power point actually. The power gain in between where the output is at 90 hertz, you go 3 dB below that, you go down to 22 dB out. The actual gain the gain at that knee frequency, the gain at that knee frequency will be 1/2 the power that it is in mid-range. And the frequency response of the amplifier goes from upper knee frequency to lower knee frequency. That is the bandwidth of the amplifier. So this concludes the second lecture for Learning Module 13.